In this video, I'm going to walk you through setting up the function generator as a square wave output, and then using the scope to characterize the voltage waveform coming out. And then lastly, and very important, we're going to characterize the voltage source. We're going to look at the two important properties of every voltage source, the Thevenin voltage and the Thevenin resistance of the source. So let's get started. First up, we're going to set up the function generator. We're going to generate a square wave with 10 kilohertz frequency and a 10 volt peak-to-peak amplitude with 0 offset. So we start out waveform. We're going to select square wave. And now we've got the parameters for the square wave. I'm going to select a frequency of 10 kilohertz. I'm going to select an amplitude of 10 volt peak to peak. And here we go. Offset is 0, 50% duty cycle. Remember what we said about the setting up the output. When we select the channel output, we get the contextual menu changing down here. And we wanted to select output load high Z. Output load high Z. That's exactly what we want. We're done. And now we're ready to look for the signal. If you notice, there's nothing appearing on the scope. That's because we need to do one last important step. While we have the output channel selected, we have to come over here and turn on the output. And now we go on. Now before we do a measurement or simulation, remember rule number 9. We want to anticipate what we expect to see. So on the scope, we should see a 10 volt peak-to-peak signal, roughly period of 100 microseconds. So let's see what we get. We turn it on. There's our signal, beautiful looking square wave on the scope. But wait a minute, it's supposed to be plus or minus 5 volts. We're getting plus or minus 50 volts. Oh my gosh, something's not right. Now, the connections between the function generator and the scope is just a simple BNC cable. I have a BNC on one end, a BNC on the other end of the cable that's connected directly into the scope. This is a 1X cable. There's no attenuation in it. How come I have the voltage coming out so much larger than what I expect? Well, that's because I forgot I don't have a 10X probe here, and the last time I used the scope I had it set for 10X. And so I need to make sure that this scale is adjusted correctly. There's no attenuation in this cable. The attenuation is 1, so I want to make sure it's a 1-to-1 setting. So I can either touch the front screen or I can touch the channel 1 button that brings up the contextual menu on the bottom. I go to the probe down here. I touch the screen that says the probe attenuation. I want the ratio, and now I can adjust it to 1, and we do enter. And now we see it's set for 1-to-1, and sure enough, look, here's the scale. So the voltage I'm displaying is the voltage coming into the scope, which is the voltage coming out of the function generator. And sure enough, it's a 5 volt amplitude, plus and minus 5 volts, exactly what I wanted to see. While we're here, we'll do two other things to analyze that signal. Let's make it a little bit bigger so that we get a little bit more of the scale. And one of the other figures of merit that we would like to get is the rise time and the fall time. Well, of course, I can't see what that is on this scale. I need to expand out the time base. So here we are expanding out the time base, and now we expand about 0, and there we go. And now I can literally read the 1090 rise time off the front screen. We're not looking for high accuracy, we just want a rough idea. 1090 rise time, it's about a division here, and maybe a little bit more of a division. This is 5 nanoseconds a division, so it looks like roughly about 7 or 8 nanoseconds as the 1090 rise time. And now lastly, we can get the fall time. Well, how do we get the fall time? Yeah, I can move the signal way off, and so I can look for the falling edge, or much more simply, I just trigger on the falling edge. So we touch the controls for the trigger. We're triggering on the rising edge. We're going to select that as the falling edge, and instantly we've got the falling edge on display. And what's the 1090 rise time? Again, let's see, we're about 5 nanoseconds of division. It's something in the order of about 8 or 9 nanoseconds. So we've got an idea of the features of this square wave that we're measuring. Based on what we have measured with the scope, we have about a 5 plus or minus 5 volt signal. So it's about a 10 volt peak to peak signal. It's a period of, let's see, we have 2 divisions. We have we have 50 microseconds, another 100 microseconds, 1 over that, 10 kilohertz. We get a rise time about 8 or 9 nanoseconds. We're going to avoid the use of the measurement functions. We're going to turn those off. Instead, we're going to use the cursor. And now we're going to manually move the Y2 value. So we're going to highlight the Y2 setting, and we're going to manually move it. So we touch it on the screen to highlight it. That's the one we're dealing with. We can use the arrows to move it around, or we can use the knob on the cursor knob on the scope to get us that value. And so that looks like it's pretty well centered there, 4.95 volts. There's a limit to how accurate we can measure a voltage. In fact, if we just eyeball it, if we move it up and down, that's like 100 millivolts is just that small amount. And so there's some error, some uncertainty in how well we can measure that amplitude. So we just have to accept the fact that, there's a little bit of an error bar there on how well we can measure it. So I'm eyeballing the center of the amplitude, and we can read right off the front screen what the cursor value is at the very bottom here. It is 4.92 volts. Okay, so that's the amplitude of the waveform coming out, and that's above 0. Now we've got the waveform fully characterized. The next step is we're going to look at the properties of the voltage source. When we think about voltage sources, we think typically as a 0th order model. The absolute simplest model of a voltage source is it's an ideal voltage. And one of the properties of an ideal voltage is the voltage output is always constant. It doesn't change no matter what the load is that we apply. And so right now it's set for 4.925 volts. And so we might assume that as an ideal voltage source, no matter what resistive load, no matter what current draw we put on the output of the voltage source, that voltage is going to be constant. It's an ideal voltage source. And to 0th order, that's a pretty good model. And as long as we have a very small load, in other words, we have a high resistance, so we're not drawing a lot of current, that's a pretty good model. But as soon as we start drawing some current, we're going to find that model breaks down and we need a better model. And that better model, that 1st order model, is a Thevenin voltage source model. And let's take a look at what we mean by that Thevenin voltage source model. We said the 0th order model it's just a voltage source. There it is. That is how we're going to think about a power source, a voltage source. And that voltage coming out is constant. No matter what resistive load we attach, this 0th order model for an ideal voltage source says we're going to get the same constant voltage. That's not exactly how real voltage sources behave. Instead, a better approximation, that's why we call it a 1st order approximation, is it's the ideal voltage source plus an output series resistor. We have 2 terms that characterize this voltage source. There's the Thevenin voltage and there's the Thevenin resistance. This means that as long as we apply a resistive load here, where that resistance of the load is really large compared to the Thevenin resistance, we've built a voltage divider, and if this resistance is really large compared to this resistance, this voltage that we measure here, the loaded voltage, that voltage is going to be pretty darn close to the Thevenin voltage. As a voltage divider, if this term here is really large compared to this one, then this voltage coming out here is going to be really close to the Thevenin voltage. But as we make that load resistance smaller and smaller, and we start drawing current, we're going to get some current draw through that Thevenin resistance. That means we're going to have a voltage drop. And what we measure on the output is not going to be the same as the Thevenin resistance. In fact, what we measure on the output, the load voltage, it's a voltage divider. It's going to be the Thevenin voltage times the resistance of the load divided by the Thevenin resistance plus the resistance of the load. And now we see that as the load resistance gets smaller, the load voltage decreases as well. And we can use this if we know what that Thevenin resistance is and the Thevenin voltage. We can predict what is that voltage output going to be for any load resistance. How do we get these two values that fully characterize our source? Well, how do we get the Thevenin voltage? Really easy. We make the load resistor really high. And that's what we've done when we did the measurements with the scope set for 1 meg input. When this is 1 meg, it's effectively open, and the voltage we measure is the Thevenin voltage. And so we get the Thevenin voltage with 1 meg input, and that Thevenin voltage is the voltage that we measure in the scope. How do we get the Thevenin resistance? Well, we have to apply a known resistive load, and we want to make one that's large enough so we have a reasonable voltage drop. And so something on the order of what we estimate or what we think the Thevenin resistance might be, if we can make the load resistance on that order or a little bit higher, then we'll be able to get a large voltage drop, and we'll be able to measure the Thevenin resistance. Because fundamentally, to get the Thevenin resistance, that is just the voltage drop across it. I'm going to call that the delta V, divided by the current through it. And what's the delta V? Well, this voltage isn't changing. That's the Thevenin voltage. This voltage we're going to measure. And so the delta V is the difference between those two. So it's the Thevenin voltage minus the load voltage. That's the voltage across the Thevenin resistance divided by the current through it. And what's the current through it? The current through it is the same as the current through the load resistor. They're in series. And that current is the voltage across the load resistor divided by the resistance of the load resistor. And that's the current through the load resistor. That's the current through the Thevenin resistor. So we'll just put the I down here. So that's the voltage across the load, and we'll bring the load resistor up above. And there we are. And this is how we're going to measure the Thevenin resistance. We're going to measure the Thevenin voltage, open circuit, and we've got that. That was our 4.925 volts. We're going to add a load resistor. We're going to measure that loaded voltage, and we're going to know what that load voltage is, and then we're going to back out the Thevenin resistance. Well, what load resistor should we use? Well, as a rough guess, as a starting place, we'd like to keep the power consumption in that resistor less than maybe about 0.1 watts. If it's more than that, it's going to get warmer and maybe even hotter, and so this will be a safe value of power consumption. The power consumption in a resistor is V squared over R. In our case, our voltage amplitude is 5 volts, so that's going to be 25 is the 5 volts squared divided by the load resistor. And so what value load resistor does that come out to? That says the load resistance we want to use should be greater than about 25 divided by 0.1, or about 250 ohms. So a good starting value might be on the order of about 200 ohms for that load resistor. So let's try that experiment. We're going to connect a load resistor of about 200 ohms across the output of the function generator, and we're going to measure the voltage change without it, in other words with the 1 meg input to the scope, and that's going to give us the Thevenin voltage, and then we're going to add that 200 ohm load, and that voltage drop is going to tell us how much Thevenin resistance we have at the output. In order to do that, I can't use my BNC cable. I need to add a mini grabber to the end of the BNC so that I can connect it to a resistor. So let's try that. Now we've got it as a mini grabber, and so we can connect our load resistor across here, and we're going to want to measure the voltage across that resistor as the output voltage. And to do that, we're going to connect the 10x probe into the scope. Now remember, when we have the 10x probe in the scope, we have to do the opposite of what we did. We have to change the attenuation setting for the scope to bring in the fact that we have the 10x probe connected. So we come to the scope, we can push the menu item on the right hand side of the screen. We want to select the summary. That brings up the attenuation in each of the channels, and we're just going to literally touch that control on the front of the scope. It brings up the attenuation dialog box, and we're going to make that 10:1. And now we are displaying on the front screen the tip voltage at the tip of our 10x probe. And we know that we have a really high input impedance. We have a 9 meg resistor in here. We have a 1 meg in this. We have 10 meg ohms of impedance at the tip of the probe. That's not going to load down our circuit. So the first measurement we're going to do is the unloaded voltage across the function generator. So we have the connection over here between the signal coming out and the ground return. And now let's look at our scope and let's see if we can't see what that signal is. So I'm going to increase the scale, and there we go. And we're triggering in the middle here. And you know what? This is pretty darn close to what we had before. It's not exact, and you'll notice, let's see, here is the 0. We've got it set for falling edge. Let's look at the rising edge initially. Here's our rising edge. You'll notice it's not a perfect square wave. It's not exactly the waveform we had before. Remember, we were measuring 4.92 volts as our amplitude, but you can see on the screen that's not exactly what we've got now. The calibration is a little bit off. Now, one of the things that we can do, remember when we compensated the probe, we adjusted that little capacitor in order to balance the high and the low frequency. We can do a little bit of a tweak. Now that we know roughly what that direct signal is, we can tweak it just a tiny bit. I'm adjusting that screw, and hey, now we're getting pretty darn close to the voltage that we measured with the coax cable directly. So it's just a little fine adjustment on the voltage, fine adjustment on the calibration of the probe. Not necessary. Again, there's a limit to the accuracy we can get with one of these scope probes. Now we've got the measurement with the probe corresponding to the measurement with the coax cable. If we zoom in on the rising edge, we'll notice another small anomaly. Let's zoom in and look. We have some ringing here. We didn't have that when we looked at the signal with the coax. And that's because we've got this whopping big loop over here, and that's distorting the signal. This is the first example we've seen where the electrical properties of the interconnect affect the signal. This interconnect, for this rise time, that's roughly the 8-9 nanosecond rise time, the interconnects are not transparent at this rise time. And you can see that by changing that loop, by adjusting it. Look, I'm affecting that signal coming out. I can change the shape of the loop, and I will adjust that ringing that we see. Now, for now, it's okay. We'll figure out a way around that later. But you can see that, yep, the geometry of that loop, the physical interconnects, are affecting that signal. For now, that's okay, because we're looking at mostly the DC level. While we're here, there's one other trick that I find useful to take advantage of. We have a pretty good looking signal. This waveform coming out of the function generator, pretty clean square wave. And we have a pretty good connection between the signal and return. We're going to take this waveform and we're going to change the interconnect. We're going to do things that are wrong. We're going to make an error, but a known error, in order to see the signature of its impact on the measurement. I'm going to disconnect the return connection. Suppose that we didn't have a good ground connection. What would the signature of that signal look like? And here it is. I've disconnected the ground. I still have the signal connected, but I don't have the grounds connected. And look at the signature. We have all of this noise on the signal. Remember this, because if you see a situation where you have this much noise and it looks like this, chances are you don't have a good ground connection. You say, well, wait a minute, how is it possible to get a voltage measurement on the signal? We still get that roughly, plus or minus 5-volt signal. How is it possible to get that 5-volt signal if we don't have a ground connection? They're disconnected. And that's because the function generator is plugged into the power strip. The earth ground is connected to the chassis ground, and the chassis ground is connected over here of the function generator, and exactly the same thing in the scope. The earth ground is connected to the chassis ground of the scope, and the chassis ground of the scope is connected to the BNC shield. And so we are making, even though we don't have the physical connection between the two grounds over here at the tips, they're still connected in a long meandering path through the earth ground and then coming back to the other scope. So there is a DC path. It's just a really long cable. It's a really long path. We've made a whopping big antenna, and we're really sensitive to RF pickup in the environment. And that's why we always want to make a good connection here so that we eliminate that large antenna. We still have a bit of an antenna here, and we saw the impact of that giving us that higher inductance in series. Still causes a problem, but for these measurements we're going to live with that so that we can separate out the signal ends and connect a resistor across those ends. This is a very common technique that we'll use over and over again, which is when we have a good measurement, we're going to purposely make an error, look at that signature, and then if we ever see that signature of the signal later, one of the first things we're going to look for is maybe we don't have a good ground connection at the tips. Now we're ready to test out this idea of adding a roughly 200 ohm resistor and looking at the voltage drop in the signal. So the exact value of resistance is not as important as knowing what it is. If 200 gives us about 1/10 of a watt, a 100 ohm resistor is going to give us about 0.2 watts of power consumption. And 0.2 watts is still not so much. And so I look at my selection of resistors I have available, and I have a nice 100 ohm resistor, and so we're going to use that knowing that the power consumption is going to be about 0.2 watts. Maybe we might feel a little bit of warmth. So I have a 100 ohm resistor, and we're going to attach it between the signal and the return. We're going to put a load on the function generator. Now I don't have the connection yet, so we don't have that load, and so we're looking at still the voltage from the function generator with no load, or the 9 meg in the scope that's basically open. And so what is it that we're measuring now? We're measuring the internal Thevenin voltage of the function generator. Now I'm going to come along and connect that 100 ohm resistor across the output of the function generator and watch what happens to the output voltage. We ought to see it drop. Oh my gosh, did you see that? Here it is open, and here it is with the 100 ohm resistive load. Why did the voltage drop? That's because we've got an internal resistance of some amount. When we put that 100 ohm load on the outside, we drew some current. That current through that Thevenin resistance gives us the voltage drop at the output. And now let's see what that is. Because remember, the voltage, the Thevenin voltage that we measured, we disconnect the resistive load. That Thevenin voltage, using the cursors here, is 4.925 volts. Now we add the 100 ohm resistor load, and I'm feeling it. I'm not sure I feel any warmth at all. We're in good shape with that. And now the loaded voltage is, again using our cursors, we'll move them down and read it off the front screen. There it is 3.275 volts. We can calculate the internal Thevenin resistance. The Thevenin resistance is, let's see, it's the 100 ohms times the Thevenin voltage, 4.925 minus 3.275 divided by 3.275. 275. Now, before we get our calculator out, which we will, we can just do a rough quick estimate. I look at these numbers here, and what's the difference here? See, it's about 1.7, roughly. And that's 1.7, and this is 3.2, 3.3. That's about a half. And so here's 100 ohms times a half. That's about 50 ohms. So we're going to expect a value of the Thevenin resistance about 50 ohms. Now we can try it with our calculator, get a little bit better answer. And this is 100 ohms times 0.504. And what does the resistance come out to? It comes out to 50.4 ohms. Pretty darn close to 50 ohms. Again, remember, part of rule number 9 is also, before you use a calculator and you type in 3 or 4 digits, always estimate so you have a rough idea. It's really easy to think you're typing 4.925 and maybe you type in 9.425. And so you want to have a rough idea of what to expect so you can compare your answer to what you anticipated. And again, it's just a good consistency test. So now we know what the output resistance of the source is. We have got a good first order model for our power supply. In this particular case, that Thevenin voltage is 4.925 volts and the Thevenin resistance is pretty close to 50 ohms. This is a technique we will use over and over again to measure and characterize power sources. If we know the Thevenin voltage and we know the Thevenin resistance, now we can predict its behavior in lots of different situations.